In terms of data centers, building a 2 megawatt reference design, how do you scale that? Well, you just clone that. We've obviously gone way past that. We've got Meta talking about gigawatts scale centers and then even clustering them. So what technologies and capabilities are required to really make this happen?
There's a lot to unpack in that question because there's a lot of different factors going on.
Today's guest is Raul Martynek, CEO of DataBank, which operates the largest geographic footprint of data centers in the US. With 450 megawatts of installed UPS capacity across 65 facilities, the company is now scaling further with nearly a gigawatt of new capacity underway.
In 2020, we spent about 200 megawatt hours on data centers. In 2025, it's about 413. So it's doubling every 4 years. It's a straight line extrapolation. Does it end? How does it end? It doesn't go forever, right?
This is based on, obviously, a company called Nvidia and their GPUs, right? They consume, 5 to 10x more power than a comparable CPU chip. And that's really what's driven kind of this need for more power. I guess the question is, over the long term, what happens to that architecture? I mean, there are a number of emerging architectures from companies like SambaNova Systems and Groq that have silicon architectures that are able to do the rendering of these large language models with a power factor that's 5 to 10x lower than a comparable NVIDIA GPU. I like to say that data centers are basically a vessel for technology adoption, and humans, in my view, are addicted to technology.
I think there's also been some work showing how many billions of liters data center uses in water. Do you see any kind of replacement fluids or new designs that would actually obviate that, make it easier on resources?
The industry is really moving to a much more water efficient, where we use a closed loop system, like the one I described with water to the chip. When you're using a closed loop system, you're using almost no water.
People are saying for some of these hyperscalers, we should be thinking about $12 million per megawatt. Does that cost come down, and how does it come down? How do you break it down? Because you still need your UPS supplies, you need your backup, you need your cooling.
I think what happens there is there's going to be
Hey, welcome to FutureScaleX's Built to Scale series, where we speak to thought leaders and industry experts about scaling inventions, innovations, and markets. Today, we're pleased to have join us Raul Martynek, CEO of DataBank, a leader in data centers. Welcome, Raul, and please tell us about yourself and DataBank.
Thank you, Kevin. Thanks for having me. It's a pleasure to be here. I've been in the internet infrastructure space for over 30 years, since the advent of the commercial internet back in the mid-90s when, we started with dial-up. I've been running businesses with institutional sponsors over those 30 years. So I've run businesses in telecom, in fiber, in cell tower infrastructure. And then about 15 years ago, got more into cloud and data centers. So it was with a cloud business at the early days of the cloud eras. And the last 15 years or so, I've been working in data centers specifically. I'm currently the CEO of DataBank. We are the largest geographic footprint of data centers in the US. We have about 450 megawatts of installed UPS capacity across 65 data centers in 26 US markets. And we're in the process of building an incremental 800 to 900 megawatts of new capacity across that footprint.
Wow, fantastic, fantastic. So given your experience in the industry then, now, today, most people really only think about data centers in connection with AI and energy needs, but as you just pointed out, it's been around for quite a while. So from your perspective, how did we get to where we are today and where are we headed?
Yeah, that's a great question. So, you rewind to 30 years ago, kind of where the internet started. I mean, there really weren't that many data centers. And in fact, I like to make a joke that, 30 years ago when I was selling telecom services in Manhattan, every office I went into had a data center. It was called a computer room, right? In the early days, the digital footprint of companies just wasn't that big. So they kind of kept it on premise, as we say, right? And as obviously what happened is, we continued to consume more technology. Businesses got more digital. They needed more storage, more compute, more networking. Those services became more mission critical. So really it was after the dot-com era, kind of in the mid 2000s, when people started outsourcing their data center requirement to third-party developers like a DataBank. That's when Equinix was started. That's when Digital Realty was started, which are kind of the two public companies. So, and fast forward to today, and obviously along that way, we've had mobile and the mobile explosion, right? We've had public cloud evolve. And what's happened is all this new technology has to go somewhere. So I like to say that data centers are basically, a vessel for technology adoption, right? And humans, in my view, are addicted to technology. So as more and more technology gets adopted, you need more and more data centers to put that equipment in there to store all that information, the videos, your emails, your remote work, obviously all the applications we use. So and then obviously, as you just mentioned, they were kind of largely in the background until 2 years ago when ChatGPT showed up and people, really got to hear about data centers because Jensen always talks about, the data center is the computer, right? And all these new pieces of equipment, which are GPUs that are built by NVIDIA, they also have to go into a data center. So it's what's really created, a significant amount of demand in our sector.
I love that analogy of the data center is the computer. I was having a conversation with someone at Schneider Electric, and he was reminiscing about the days when he was building a 2 megawatt reference design. And when somebody asked him, how do you scale that? He said, well, you just clone that. We've obviously gone way past that. We've got, Meta talking about gigawatts scale centers and then even clustering them. So, what technologies and capabilities are required to really make this happen?
Yeah, no, that's a great question. And you're absolutely right. Data center requirements as measured in kind of the amount of power that customers want has increased significantly over the last 10 years, right? When I got the data bank about 10 years ago, the largest enterprise deployment was, a 2 megawatt type of deployment. We're having conversations with major banks that they're looking for 90 megawatts to support their digital infrastructure. From a technology perspective, what's kind of interesting is it's very much similar from what it was, right? Because ultimately, a data center is a vessel, it's obviously a building, it's special, purposely built to house this computer equipment. It's the computer equipment that consumes the electricity. We call that the critical load. And then there's two major functions that a data center has, right? One is to provide that power uninterrupted way. And the second is to cool it, right? So we have to deliver power and then we got to dissipate the heat. And from that perspective, those technologies, while they've evolved, they're still relatively, the challenge is still the same. Nothing has changed other than you need more power in a given facility. So the innovations are really around, how do you reduce the amount of energy that you need to cool that data center? It's measured in a term that we call PUE or power utilization effectiveness. And, 10, 15 years ago, you used to have a data center that, let's say it had a megawatt of critical load. It would also need a megawatt just to cool and power the data center. We've been able to improve that over time, significantly. Most data centers today have a 1.2, 1.3 PUE. In other words, they only need 20% or 30% more electricity to power and cool the critical load. And that efficiency is really where all the innovation has gone on. In the last 5 years, we've gone from, master planning 20, 40 megawatt data centers to master planning 60 or 72. We actually have a data center project in Virginia where one of the buildings is scheduled to be 120 megawatt data center campus, right? Or building. So it's just, a lot more of that equipment, but the base kind of technology has remained the same. It's just gotten a lot more efficient.
Oh, okay. Well, if we have time, I'd love to go into electrification and heat management because that seems to be a really big issue, not just for data centers, but for manufacturing as well. But let's talk about this access to power, right? We're hearing a lot about the need for green power. If you look at what the IEA is saying, they're saying that as a world, we need to invest trillions of dollars by 2030, 4% rate per year. They're estimating 80 million kilometers of new cabling, and that's for transmission and distribution, right? But to put that in perspective, or the way I think about it, the US has been investing at a rate of about 1% per year into the grid. So, do you see a problem here with power to X and data centers or just the entire grid itself?
Yeah, I mean, look, there's no secret that, there's a lot of talk about, power shortages and constrained power. And you've had markets like Ashburn or Santa Clara in California, which is a big market, or Salt Lake, where they've had to put freezes on new connections to the grid because they've quote unquote run out of power. I mean, taking a step back, I mean, the reason we got here is because if you actually look at power consumption in the US, over the last 20, 30 years, it's been flat, right? I mean, you've had new generation and a transition to more renewable power, but because of efficiency gain, broadly speaking, the amount of megawatts or gigawatts, the consumed was relatively flat. Now, because of not just data centers, but, onshoring of manufacturing, obviously a transition to renewable battery plants, there's a lot going on in this transition that has now created an increase in demand for electricity that people are saying is, 2 to 3% per year, which doesn't sound like a lot, but measured on the scale of the US power grid, it is a lot. And because of that flat demand for the last couple decades, utilities really didn't invest in new transmission or new generation. It was more about shifting between fossil fuels and renewables. So absolutely, I think there needs to be a significant amount of investment in the grid, not just to power, the AI revolution, but also to accomplish which, still a goal for a lot of folks, which is a transition to a clean energy economy. And certainly any of the efforts around, bringing back manufacturing to the US or, you know, improving kind of the manufacturing base in the US is going to result in more and more power needs. So that's what's currently the utilities are facing is they have these forecasts. These forecasts are significantly more up and to the right than what they've been accustomed to. And the challenge is that, the electric grid doesn't move in a monthly cycle. It moves in years and decades, right? So this transmission lines and power generation and distribution, these things are 5, 7, 10-year type of projects when everyone wants that power yesterday.
Yeah. So, well, we can spend a lot of time talking about permitting and things like that, but let me bring back some of the IEA data. So, and looking at what they're saying is that in 2020, we spent about 200 megawatt hours on data centers. In 2024-25, it's about 413. And in 2030, they're estimating 945. So that's doubling every 4 years. It's kind of like a Moore's law, but for data center energy usage. And it must find its analog somewhere on the hardware solution side. So, but the straight line extrapolation, does it end? How does it end? It doesn't go forever, right?
If I knew the answer to that question, Kevin, I'd be on a Caribbean island somewhere. But no, it's another great question. And ultimately, yeah, I mean, right now the prognostications that you just pointed out are, a significant amount of incremental demand from data centers, AI, and kind of the adoption of this technology. As we briefly talked about earlier, this is based on obviously a company called Nvidia and their GPUs, right? These GPUs are parallel processors. So they're different than CPUs in that they, are really good at processing in parallel at scale. And the defining feature of them is that they consume, 5 to 10x more power than a comparable CPU chip. And that's really what's driven kind of this need for more power. I guess the question is, over the long term, what happens to that architecture, right? I mean, there are a number of emerging architectures, silicon architectures from companies like SambaNova Systems and Groq, Groq, not to be confused with Elon Musk's company, Cerebras Systems, a new business called Positron that have kind of silicon architectures that are able to do inference, which is kind of the rendering of these large language models with a power factor that's 5 to 10x lower than a comparable NVIDIA GPU. So it will be interesting to see, will the industry adopt more power efficient architectures and that will reduce some of that power demand? I mean, I think it's inevitable because efficiency always wins out. I do think, though, that, AI as a new technology, because it's a general purpose technology, has unlimited application across everything we do, kind of similar to the internet, right? I mean, you could argue that obviously before the internet, there was very little power being delivered to data centers. And now we're at, globally, what they say, 2, 3, 4% of global power is consumed by data centers. So I would definitely believe that we're going to be using more power in the future. But I think these estimates just are assuming that there's going to be no improvement in the power efficiency of these chips. And that I just don't see happening. So I think potentially, we're going to be, we're not going to have to deliver as much power as we want, but certainly that day isn't here today, which is why there's so much stress on kind of the grid and the need to get more power as soon as possible.
Great. And you did mention some novel architectures, and I do want to ask you about that. But before I get to that, there's a lot of discussion about 24/7 CFE. Everybody wants green electrons, in addition to guaranteeing the uptime and being resilient. And there seems to be a lot of discussion about microgrids, nanogrids, mini grids. What are your thoughts about that? Can we actually have green electrons and all that power that we want?
Yeah, there's a lot to unpack in that question because there's a lot of different factors going on. As you well know, look, over the last 5, 6 years, I mean, there's been, just a tremendous amount of new renewable energy generation that's occurred on the grid. I'm based in Texas, which has its own power grid. It's called the ERCOT system. You go look at the ERCOT real-time dashboard on any given day, 45% of the entire electric consumption in the state of Texas comes from solar and wind and battery and hydro and nuclear, right? So the state of California has, significant amounts of renewable power consumption and generation that comes, on the west side of the state. So there's no doubt there's been just a significant amount of new renewable energy. DataBank itself, we have a mandate, a 2030 corporate mandate to get to 100% renewable. As of last year, we were at 65% across our portfolio. So it was encouraging to see that, as a developer of data centers, that we could avail ourselves of these products. Obviously, the new administration has a different view on that, and it's yet to be seen, like what happens to all these projects that happened under the prior administration as they're now coming into fruition. And then there's obviously a lot of talk about, doing generation through natural gas, which is kind of a short-term thing, and then nuclear. You know, I think that, on the microgrid side, that's been another thing that, people talk about a lot. But there's some significant challenges there from a data center perspective, right? When you generate power on site through typically gas turbines, these turbines weren't meant to run, 100% of the time, right? They need maintenance. That means you need to over provision. The majority of these installations were done from an oil and gas perspective, where again there wasn't a requirement to be 100% of the up all the time. So what we see is most of our customers, especially the hyperscalers and ourselves, we want to be connected to the grid. We want to have the redundancy, the resiliency that comes with a grid connection. And really, we think the solution is about connecting more generation to the grid and increasing the amount of transmission where there is generation to pockets that want to consume it. So those are the ways we see it, best being solved. I do think you're starting to see, especially in some of these remote AI training locations, there's the well publicized, about Stargate. It's an Oracle open AI location in Abilene. That does have some on-site type of generation because that was a Bitcoin type of area in West Texas that was using, natural gas that was being generated there to propel turbines to be able to create power. So there is some pockets where it's being used, but we don't see it being widely adopted because of some of those challenges around reliability and durability.
Oh, okay. I once had a conversation with a director at RPE about their cooler chip program. And as you mentioned, Raul, it wasn't just about new chip designs, but also keeping pace with advanced liquid cooling systems. And I noticed that you guys are already installing some of that in your latest site. So maybe you could tell us a little bit about the need for both air and liquid cooling strategies.
Yeah, absolutely. So, in data centers, obviously, as I mentioned, one of the key functions is to cool that equipment. And as you pointed out, up until now, air, you're blowing cold air, into a cold aisle or into the racks was the predominant way to cool this equipment. When we talk about power and density, we talk about power density. In other words, how much power we have to deliver to a rack. And with air cooling, you could comfortably, cool, 20, 30, 40 kW per rack. But what's happened is with these Nvidia GPUs, they're much denser type of architectures that require 50 or 75 or 100 or more than 100 kW per rack. And at that point, you just can't blow enough cold air, practically to be able to cool that. So that's why the industry has shifted towards water cooling type of designs that predominantly take two forms, either one where it's water to the rear door. So it's kind of like a radiator in your car, and there's chilled water through that, and the servers are pulling air through that manifold or through that radiator and cooling itself that way. And then the more advanced way, when it gets even, greater densities, is water to the chip. So it's basically a type of configuration where the chips themselves have a manifold on them with, a set of tubes that are bringing in cold water, and the heat from the chip is, being transferred to the water, and then it gets pulled back out from the server rack, goes to a chiller plant where it extracts the heat from that water and then recirculates it again. And we're seeing power densities of 130 kW per rack there. And NVIDIA has a roadmap that says that they're going to need to go to 600 or 800 or 900 kW per rack, which I will tell you leaves a lot of us in the data center sector feeling very uncomfortable because that's a lot of heat in a very small area. And one hiccup is, could cause, catastrophic damage to that equipment or to the space around it because of just the immense amount of heat generation. So that's a couple years out. We'll see how it evolves. We'll see how these chip designs evolve. Again, I'm optimistic that, some of these more power efficient architectures will take hold and we won't have to, push the limits to that extreme on this power density.
This is clearly a side question, Raul, but in terms of data centers, I think there's also been some work showing how many billions of liters data center uses in water. Do you see any kind of placement fluids or new designs that would actually obviate that, make it easier on resources?
I'm glad you asked that question because there's a lot of confusion about this topic out there. So let me try to unpack it and shed some light on it. So I mentioned PUE, which is kind of how we measure the efficiency of how we use electricity. There's also a comparable term. It's called WUE, which is water utilization effectiveness, which is how many gallons of water do we use to cool a data center. About 10 years ago, there was a trend towards, on the cooling side, something called evaporative cooling. If you've ever driven around a city in the winter, you'll see like this steam coming off the top of skyscrapers. That's because at the top of that skyscraper, there's a chiller plant with an evaporative cooling tower. And what's happening is the hot medium that has, been circulated through the building to cool the building goes up to that cooling tower, and then they drip water to extract the heat from it. So it's a very efficient cooling technology from an electricity perspective. It's very inefficient from a water perspective because it evaporates a lot of water. That's a design that, there are some people, some hyperscalers who still use that design, but the industry is really moving, and certainly players like DataBank have already moved years ago to a much more water efficient, where we use a closed loop system like the one I described with water to the rear door or water to the chip. When you're using a closed loop system, you're using almost no water. So our data center sites, we only have about a dozen of our 65 data centers that were kind of inherited through acquisitions that have some of that evaporative cooling technology. We've never installed a new one in the last 7 or 8 years. So most folks in the industry are using these very water efficient cooling technologies. You do still have some of this water inefficient cooling technologies. And I think the thing to do is, if there's a concern, you need to ask the question, what type of cooling technologies that they're center planning to use? And that's why, by the way, you can build data centers in Phoenix, right? Because even though it's a hot climate, if you're using like a closed loop system, like I described, you don't really need a lot of water. And that's why it can still be efficient, even in a climate like that.
Let's shift gears a little bit. We hear the syllogism a lot about energy for AI, which we've been talking about, but we also hear things like AI for energy. And I'm thinking in particular some of the data that's been coming out from Bloomberg about Whisker Labs, about the Iberian Peninsula, about some of the behind the meter data that they've been producing that says, hey, listen, the voltage and frequency fluctuations throughout the grid are actually exacerbated by the presence of data centers. It's like kind of a gravity center, and then it sort of sucks all this power, and everybody else is dealing with the fluctuations. And they're predicting billions of dollars in equipment damage if we don't solve this problem with the proliferation of all these data centers. I mean, what are your thoughts about that?
The reason those stories, so as we talked about, data centers have been around for a long time, and we've never heard that story before. Why are we hearing it now? Well, the reason we're hearing it now is it is a truth that these new data centers with AI equipment in them, with GPU equipment in there, especially around training, where you train a model with large amounts of data and use thousands or tens of thousands of GPUs to kind of act as a single computer to train that large language model, that those clusters seem to exhibit this up and down frequency fluctuation that prior workloads did not have. I will tell you, you look at the power graphs of our data centers today, and they kind of look like a dead patient. It's just flat because the computer equipment's on, it's basically always on. Yes, one processor is going up when one's going down, but over thousands and tens of thousands of processors or storage arrays, it tends to balance itself out, and hence why you have a relatively stable power grid. In fact, data centers were always liked from a utility perspective because we did have this predictable power profile. Some of these new AI data centers are different, and you're absolutely right. They are exhibiting strange kind of characteristics from a frequency perspective, from a variable use perspective, and it can cause, issues on the grid. So right now, we're aware of two utilities: Dominion Energy in Virginia, which is obviously the utility that's supporting the largest constellation of data centers in the country, plus Encore and ERCOT in the Texas utility. They both have proceedings going on to understand, what are the risks associated with these kind of large AI training data centers, and how do we make sure that they don't cause problems to either equipment in the rest of the grid or to the grid itself, as you just pointed out, through a blackout type of scenario. So, look, I think this is all happening now because most of these AI data centers have only just opened up, right? I mean, ChatGPT was only 2.5 years ago, or 2.9 years ago. So, and it took about a year for people to get moving on it. And now you're starting to see the first generation of these data centers that were kind of being built for AI come to market. And now you're seeing their characteristics of their workload, as we call it, and its potential impacts on the grid. So, look, I'm pretty confident that, the industry can figure this out. I mean, it's in the data centers, developers, interest to figure that out, the hyperscalers' interest, and obviously the power utilities. So but it's going to require some collective effort to get to a solution.
Oh, okay. And so maybe I'm over extrapolating, but if it's really about training, then basically maybe over a larger timescale, this is just a blip. And as AI matures, these sorts of things, these power drawdowns and variabilities that you're talking about, will basically even out across the entire grid.
That's a decent thesis. Absolutely. I mean, it's yet to, who knows? I mean, look, we're going to be training models for a long time. What you don't know is, are these models going to continue to get bigger and bigger, or are people going to focus more on algorithmic improvements to make them better, right? Today OpenAI had its launch event with ChatGPT 5. I was watching some of it. They didn't talk at all about like the number of parameters, how big the model was. They were talking more about, hey, the model understands, what type of question you're going to ask, and then kind of leverages different parts of our different model ecosystem to come out with the better answer. That sounds to me like, hey, we're focusing more on efficiency rather than brute force of, hey,
Yeah.
let's make it bigger to make it better.
Right. And you mentioned earlier some of these interesting companies and architectures. I'd like to kind of dive into that. I was just looking at Nvidia's stock price in 2018. It's hard to believe it was under $10. And it was because they were visualized and valued as just a kind of GPU company, basically pattern recognition, videos, and things like that. But it kind of dawned maybe on the market later that, hey, what is intelligence other than pattern recognition, right? And if you do that over and over again, you can train these things. But you're saying that there could be a revolution in chip design that actually draws down a lot more power, I don't know, 5 to 6x maybe. But maybe you could go into that. Like, is this really transformative, like another NVIDIA event on the horizon with some of these companies? What is the impact to you as a data center operator, owner, and leader?
Yeah, listen, I mean, I find this fascinating because obviously, as a kind of a business that supports technology adoption, we really keep a close eye on what type of technologies are being adopted by our customers so that we can build a better data center to support that. I mentioned some of these companies: SambaNova Systems, Groq, Cerebras. What they've done is, as you pointed out, NVIDIA and its architecture really came from video games, right? Rendering, pixels on a screen, right? And it had to do that in a parallel way, which is hence why it was good at parallel processing around neural networks that required computation at a massive scale on a parallel basis. So that architecture was designed for one thing and adapted for something else. And today, large language models and the architecture behind them, transformer based large language models, it's a pretty well known architecture. So these companies a couple of years ago said to themselves, hey, let's build a piece of silicone in a silicone stack that's just fully optimized to, you know, compute the output for a large language model to spit out, as they say, tokens, right? Which is the response that comes from a large language model. And that's why these architectures are much more power efficient. In the case of SambaNova systems, their standard rack is 20 kW and it can spit out, a significant amount of tokens that, would be a larger footprint from a comparable Nvidia type of platform. So to us, again, I think that's a healthy thing for the industry. Efficiency is always good. We're going to want to drive the cost down of this technology, just like the internet, so that it can be adopted. Going back to, I remember when I got into the internet, a T1, which was 1.5 megabytes, cost $2,200 a month. It was ridiculously expensive. Right now, you have a gigabyte in your house for $80 a month, right? What that's done, of course, is it's everywhere, right? There's internet everywhere. It's in your car. It's in, in your house. It's in on airplanes, right? And that's a function of driving down that cost curve. So we think these technologies will drive down the cost curve to adopt AI, which will spawn, more use of that technology. And look, for the industry itself, I mean, that could mean, some people might perceive that as, hey, that's bad for the data center sector because the more megawatts we build, the more money we can make, right? But I look at it as long term, I think this sector will continue to advance, back to my earlier comment, because I just think that, humanity will continue to find reasons to deploy technology and uses for technology. And no one's figured out a different form factor than a data center to house that technology. So I'm fully confident that there will be more data centers, 10 years from now, 20 years from now, 30 years from now. It's really a question of how many more. And I think being efficient is a good long-term strategy.
Right. And another side question, I think out in the internet, people are saying for some of these hyperscalers, we should be thinking about, like, I think you had mentioned it to me earlier, Raul, that we should be thinking about $12 million per megawatt, something like that. Does that cost come down, and how does it come down? How do you break it down? Because you still need your UPS supplies, you need your backup, you need your cooling. How do you drive that cost down? Or you're not concerned about it? The market will actually find ways to monetize any increase in megawatt.
That's the economics of our business. Again, we are a real estate business, right? So we build this building, we do measure it in megawatts. That's a good estimate. It's about, call it 11 to 13 million per megawatt. Believe it or not, it was cheaper in 2020 to build a data center, right? Back then, we had driven costs down to about $8.5 million a megawatt. 20 years ago, it used to be 20 million a megawatt because you just didn't build that much of it. And then as more and more got built and the suppliers of the components that go into a data center got better, they built them cheaper, it brought that price down. Unfortunately, our cost to build is really driven by a lot of things. And, it's a physical building. So as you can imagine, construction costs, right? Steel prices have gone up, as you know, because of tariffs and things like that. Well, guess what? Data centers use a lot of steel. So it means that we have to pay more for steel. As labor costs go up, these are very skilled trades around electrical, mechanical, security. As wages go up because of demand, we have to push that on. So ultimately, our ability to price our product is based on cost us to build that product, which is that a dollar per megawatt. And really pricing has doubled in the last 2 years, 3 years, because of all these increased costs as a function of, the COVID supply chain things, obviously now tariffs, now demand, and also interest rates, right? A couple of years ago, we might already forgotten, but interest rates were at zero, right? And today they're at 4.5%. And obviously that means it costs us more money to borrow money to build these data centers. So those are all the factors that go into the blender of costs. And ultimately, I do think, costs are going to go up because some of the things we talked about in terms of the characteristics of these AI workloads, in terms of their potential impact to the grid, the fact that you're having all this power in one rack, which means we have to come up with secondary cooling loops to make sure if that there is an interruption, we can still supply cold water to that rack so that it doesn't shut down. All those things are going to cost more to, they're going to require us to invest more in the architecture of the data center, which is going to increase the cost per megawatt, which means our cost to the customer is going to have to be higher.
Do you see the market getting really competitive in how resilient a given data center is? Maybe this is an argument for clusters and failovers. But does that increase your cost for backup generators and energy supply? And the reason I ask this, rule is because there's a certain number of startups and, of course, some venture capital money that's going into things like thermal batteries, thermal energy storage. I think Google's been experimenting with these things and basically saying for every megawatt, we need at least 1 to 10 hours, maybe even a couple of days of equivalent megawatt backup, right? But my take is that you're very confident that you'll be able to cobble this stuff together and that it's not going to significantly increase total costs.
Yeah, the battery stuff is interesting because, a data center by definition is designed to run 24 by 7, 365, regardless of what's happening out there in the world, right? We offer 100% uptime SLA to our customers. Our customers expect 100%. So when you talk about those battery solutions that are 5 hours or 6 hours or 7 hours, what happens if you have an outage for 9 hours? Then what do you do? Right. So that is why, we see the battery technology, especially at a grid level, as being a better solution for like peak shaving, for those spikes in power, for, on the renewable side, being able to generate electricity during the day and then discharge it at night, things like that. For the most part, data centers, use a diesel generation as the primary means of backup. So we have all these diesel generators, for the most part, are sitting there idle. And, we test them once per month for, 45 minutes. But other than that, unless there's a utility outage, they don't run. But when there is a utility outage, guess what? You don't know the duration of it, which is why you want to have a diesel generator. In my career, the longest outage I've experienced was, during Hurricane Sandy in the New York area. We had to run on generation for 7 days. There was no power for 7 days. Obviously you wouldn't be able to do that on battery. So you had to rely on kind of a more traditional means of generation like diesel. And ultimately, all this diesel generation that's been installed around these data centers, the grid can use that, right? I mean, in a lot of markets, we participate in what are called supply response programs, where we opt into a tariff that tells the utility, hey, they can come to us 2, 3 times per year and require us to go on generation. And the reason they do that around those peaks, around very hot summer days, or if there's some type of disruption. And it actually is a lot cheaper for us to go on generation, and frankly, probably environmentally better for us to go on generation for a couple hours and not have to build some billion-dollar peaker plant to supply electricity for those 3 days per year when the grid needs it, right? And I think the industry could do a lot more there because at this point there is, 10, 20 gigawatts of installed generation in the US around all these data centers. We could probably use that in those very specific areas and times to relieve stress from the grid.
That's an excellent segue to my second to last question, Ro, is a lot of traditional energy companies are asking us about the axis between the data center, the energy company itself, and the utility, and new types of power purchase agreements, or even new types of business models that will evolve over time that will change the combination of hardware, software, and business strategies. As a key data center provider, I mean, what works for you? What do you see happening in the future?
Yeah, I think what happens there is there's going to be just a lot more collaboration between the energy sector and the data center sector in terms of, how do we consume power? How do we, do it in a way where we can minimize the impact to each other's, businesses? And how do we do it in a way so that collectively we can be more efficient together? So those dialogues really, I've only started in the last couple of years because, before, of course, every data center power was a critical component. But, 5 years ago, it was about 10 megawatts or 20 megawatts or 30 megawatts. Now that we're talking about 300 megawatts, 500 megawatts, gigawatts, it's clear that there needs to be more collaboration. So, yeah, I mean, you've seen it with the hyperscalers in terms of some of their moves with Microsoft in Constellation, to recommission nuclear reactors like in 3 Mile Island, or AWS's acquisition of acreage next to a Talon Energy nuclear power plant. So I think you're going to see a lot more of that, these kind of very tight, collaborations between data center developers, be they hyperscalers or players like DataBank, and power producers and distributors, so that we can align our objectives in a better way.
Okay, fantastic. Final question. Knowing what you know and what you're seeing, Raul, what are we talking about 10 years from now that we're not today?
Well, so a couple guesses there. Well, hopefully we'll be talking about small nuclear reactors. That's a technology that, again, there's been some press on that, but it's been mostly press as opposed to actuals. Based on what we have learned about that technology, we think it's very promising. It's a completely different architecture, it's very safe, and its footprint is much smaller. So I hope that and obviously it's clean energy and always on type of energy as well. So I hope we're talking about that. And then the second thing I hope we're talking about is all the kind of beneficial things that AI is bringing to the human race rather than some of the dystopian stories that you hear, right? I mean, look, here we are, it's 30 years on to kind of the adoption of the internet. And I would argue that the internet has been one of the most important developments in human history. If you think about your entire life and how it's been enriched by, the ability to communicate and to access information and to be able to learn and to collaborate. I mean, it's been an incredible thing. Obviously, there's been some bad things that have happened, but that's the human condition, right? So I hope we're also talking about AI in a similar way, where it's really been kind of a positive impact on society, and it's not, on a net basis, a negative.
Okay. Well, hey, Raul, it's been a delight to speak with you here. Thank you very much. If you'd like to talk more with Raul or FSX, please visit DataBank and/or contact us via our website, FutureScaleX.com. Thank you.
Thank you, Kevin. Thanks for having me.
Great. Thank you.